Hello dear students. So I welcome you all to this seventh session of discussion on the nuclear physics chapter. So in this session we will have the discussion on one of the nuclear reaction process called as nuclear fission on the basis of the liquid drop model. So in our earlier discussions we have studied this liquid drop model and explanation of the stability using that binding energy property, which is again based on this liquid drop model. So using the same liquid drop model we will try to understand what is nuclear fission, and after that, as this liquid drop model has certain disadvantages, so one of the main disadvantages it fails to explain the shell closure structure, means the arrangement of nucleons in the shells, just like the arrangement of electrons in the orbit in an atom. So this liquid drop model fails to explain that shell closure property or the arrangement of nucleons inside the nucleus in the shells. So in order to explain that shell closure property, we have one more model which is called as shell model of the nucleus. So we will have the discussion on that shell model of the nucleus also. Well, the nuclear fission is a process, or it is a type of nuclear reaction in which the nucleus of an atom splits into two or more smaller nuclei. So this nuclear fission is nothing but the splitting of heavy nucleus into two or more lighter nuclei of nearly equal masses. So in this nuclear fission process, along with the production of fission fragments or fission products such as the lighter nuclei, there will be release of large amount of energy, as well as it will produces certain gamma photons, as well as it will produces certain neutrons. So in general, the nuclear fission is a nuclear reaction in which the heavy nucleus splits into two or more lighter or smaller nuclei of nearly equal masses. So that is the nuclear fission. Then how to understand this nuclear fission on the basis of this liquid drop model? So in order to explain that nuclear fission process, in the year 1939, the two scientists Bohr and Wheeler gave the theoretical treatment of this nuclear fission of heavy nuclei on the basis of this liquid drop model. So in the year 1939, these two scientists, Bohr and Wheeler, gave the theoretical explanation about this nuclear fission process, which is based on this liquid drop model. So according to their study, or according to this liquid drop model, the basic assumption is the nucleus is assumed to be like a drop of liquid with certain analogies or certain similarities. So that is the basic assumption of this liquid drop model, which considers the nucleus as the liquid drop with certain similarities. Then if a thermal neutron hits the nucleus, a compound nucleus is formed with certain exciting energy due to the extra neutron. So in the neutrons, based on the energy, we have different classifications such as thermal neutron, epithermal neutron, the slow neutron and the fast neutron, means depending upon the energy, which varies from electron volt to few mega electron volt. The neutrons have been classified into different types. So this nuclear fission process happens only with the thermal neutrons. So the thermal neutrons having energy 0.025 electron volt. So such neutrons, when hits certain nucleus, generally a heavy nucleus, so because of that interaction there will be formation of compound nucleus. So compound nucleus is nothing but that nucleus is in excited state. So that excited state or the excitation energy comes from that thermal neutron interaction with that target nucleus. So this excitation energy sets up the compound liquid drop nucleus into rapid oscillations. When an extra amount of energy is added to that target nucleus, there will be formation of compound nucleus or the compound liquid drop. So that extra energy sets that compound nucleus into certain oscillations. So this diagram helps us to understand this nuclear fission process very effectively. So initially we have neutron, that is thermal neutron only. It is made to interact with certain target nucleus, that is uranium nucleus. So because of this interaction, there will be formation of compound nucleus. So that compound nucleus is in dumbbell shape. So after certain time interval, that compound nucleus which is in dumbbell shape splits into two lighter or smaller nuclei. In this case, the uranium splits into barium and krypton as the fission fragments or fission products. So along with these two fission products, there will be emission of certain neutrons. So as a result of that rapid oscillations, the nucleus takes the dumbbell like shape as shown in the figure, and due to positive charge repulsion on the two ends splits into two fragments, hence forming two daughter nuclei. So this is the phenomenon of nuclear fission, and this liquid drop model explains it very effectively. So how to explain this nuclear fission process on the basis of liquid drop model means the thermal neutron interacts with heavy nucleus, for example uranium-238. Then because of this interaction, there will be formation of compound nucleus which is having dumbbell shaped nuclei. Then because of that rapid oscillations, this dumbbell shaped compound nucleus splits into two lighter nuclei such as barium and krypton in this case. So this liquid drop model explains this nuclear fission process or reaction very effectively. So this liquid drop model helps us to understand the nuclear stability on the basis of the binding energy property. It also explains this nuclear fission process very efficiently, but it has certain disadvantages. One of the main disadvantages is arrangement of nucleons, that is protons and neutrons, in the shells, just like the arrangement of electrons in the orbits in an atom. So this liquid drop model fails to explain that arrangement of nucleons in the shells. So in order to explain that arrangement of nucleons in the shells, the second nuclear model has been developed, which is called as the shell model of the nucleus. So according to this shell model of the nucleus, the motion of each nucleon is governed by the average attractive force of all other nucleons. Means the motion of a single proton or neutron is governed by the average attractive force of all other nucleons present in that nucleus. So this results in the orbits which form the shells. So this motion of a single nucleon which is governed by the average attractive force results in certain orbits which are called as the shells, just as the orbits of electrons in atoms do. So this is similar to the electron orbits in an atom. As nucleons are added to the nucleus, they drop into the lowest energy shells permitted by the Pauli's principle, which requires that each nucleon have a unique set of quantum numbers to describe its motion. So we all know that the Pauli's exclusion principle is no two electrons can have all same 4 quantum numbers. Means no two electrons can have the same 4 quantum numbers. Just like in case of electrons, that Pauli's exclusion principle is also applicable to this nucleons also. That may be proton or neutron. So each proton or each neutron is having certain different set of or unique set of quantum numbers, which helps to describe its motion in that orbits or the shells inside the nucleus. So this is the diagram in which the arrangement of the protons and neutrons in the shells in the case of carbon 12 nucleus. So carbon 12 nucleus has 6 protons and 6 neutrons. So in this, the first shell is having 2 protons, similarly 2 neutrons, just like one s shell in the case of electron orbits in an atom. The next shell is having 4 protons and 4 neutrons. So it is very much similar to the arrangement of electrons in the orbits in an atom, just like 1s, 1p, 2s, 2p, 3s, just like the same shells. In the same shells, these nucleons are arranged in the same manner as in the case of arrangement of electrons in an atom. So this is one of the example in which the 2 levels or 2 energy levels are filled as in the case of carbon 12 nucleus. So when a shell is full, means that is when the nucleons have used up all of the possible sets of quantum number assignments. Means when the nuclear shell is completely filled or it is full, then that nucleus or a nucleus of unusual stability forms. Means when the nuclear shells are completely filled, then such nuclei are called as the stable nuclei. So when a shell is full, a nucleus of unusual stability forms, means it is stable nuclei. So this concept is similar to that found in an atom, where a filled set of electron quantum number results in an atom with unusual stability, just as in the case of inert gas. So in the case of electronic configuration, we can use that inert gas electronic configuration as the reference one. Means they are completely filled, means they are stable. So similar to that phenomenon, in the case of this nucleus also, when the shell is completely filled, then it is considered as the stable nuclei. So when these nuclear shells are completely filled, or when these nuclei are called as the stable nuclei. So for that there is one criteria, that is number of protons or number of neutrons must be equal to certain numbers, and those numbers are called as magic numbers, and such nuclei are called as the stable nuclei in which the shells are completely filled. So what are those numbers? When all the protons or neutrons in a nucleus are in filled shells, the number of protons or neutrons is called a magic number. So when the shells are completely filled, then the number of protons or neutrons of that completely filled shells are called as magic numbers. So some of the magic numbers are 2, 8, 20, 28, 50, 82 and 126. Means if any nuclei is having either proton number is equal to these numbers starting from 2 to 126, or neutron number is equal to these numbers, that is from 2 to 126, then they are called as magic numbers, and such nuclei are called as or considered as the stable nuclei. So this nuclear shell model explains the stability on the basis of the magic numbers. So what are the magic numbers? The number equal to 2, 8, 20, 28, 50, 82 and 126. So either proton number must be equal to these numbers or neutron number equal to these numbers. Then such nuclei are called as magic nuclei, which are considered as the stable nucleus. For example, the SN116, that is 10, 116, has a magic number of protons. So in case of SN116, Z, or the number of protons, is 50 and number of neutrons is 66, that is 116 minus 50. So it is having magic number of protons and it is called as magic nuclei or the stable nuclei. Similarly, in the case of iron 54, that is Fe54, it has magic number of neutrons, that is 28. So it is having 26 protons and 28 neutrons. So that iron 54 is also a magic nuclei. So it is a stable because neutron number is equal to 28, which is a magic number. Similarly, if we consider two more examples, that is calcium 40 and lead 208. So in the calcium 40, proton number is 20 and neutron number is 20. So 20 is a magic number. So it is having both proton as well as neutron number is equal to 20, which is a magic number, means it is doubly magic nuclei, which is exceptional stability, which has the exceptional stability because it is having both proton as well as neutron number as the magic number, 20 and 20. So doubly magic nuclei and highly stable. Similarly, if we consider lead 208, so it is having 82 protons and 126 neutrons. So both 82 as well as 126 are the magic numbers. So again this lead 208 is also a doubly magic nuclei and it is highly stable, means it has exceptional stability. So for example, calcium 40 and lead 208 have magic numbers of both protons and neutrons. So these nuclei have exceptional stability and are called as doubly magic nuclei. So based on this nuclear shell model study, the filled shells have total angular momentum J, or the total spin is equal to J equal to 0. Means if the nuclear shells are completely filled, then its spin or angular momentum is 0. The next added nucleon or the last unpaired nucleon determines the J of the new ground state. Means if we have to determine the spin of that nucleus, if the shells are completely filled, then they have 0 spin. Then if we add one more nucleon, that may be proton or neutron, that last unpaired nucleon contributes to the total spin or total angular momentum of that ground state of that new nuclei. So only last nucleon is responsible for that spin or angular momentum of that nuclei. So when nucleons are excited out of the ground state, they change the angular momentum of the nucleus as well as its parity. So parity is one more property of the nuclei. So when the nucleons are excited out from that ground state, then that excited nucleons changes the angular momentum or spin of the nucleus as well as its parity. So this shell model describes how much energy is required to move nucleons from one orbit to another and how the quantum numbers change. So this nuclear shell model explains the stability of the nucleus on the basis of magic numbers, that is either proton number or neutron number is equal to that magic number starting from 2, 8, 20, 28, 50, 82 and 126. So either proton number or neutron number should be equal to that magic number, then it is stable. If both are magic numbers, then it is highly stable. It is called as doubly magic nuclei. Then if the nuclear shells are completely filled, then angular momentum or spin is 0. Then if we add another nucleon to that nucleus, then that nucleus is responsible for the ground state, spin and parity of that nucleus. And this shell model explains or describes how much energy is required to move a nucleon from one orbit, means from one shell to another shell, and because of that movement from one shell to another shell, how the quantum numbers change can also be explained with the help of this nuclear shell model. So this completes our study on this nuclear models, which is the third topic of this nuclear physics chapter. So the summary of these three sessions, that is session 5, 6 and 7, is in this nuclear models we have discussed the liquid rock model and explanation of stability of the nucleus using that liquid rock model by considering the binding energy property, and after that, in order to determine the accurate values of binding energy, we have discussed the semi-empirical mass formula which was given by the scientist Weizsäcker, and after that we have also discussed in today's session, that is the nuclear fission process on the basis of liquid drop model, that is splitting of heavy nucleus into two or more lighter nuclei. So this is about the liquid drop model. It can explain the stability on the basis of that binding energy, but it fails to explain the shell closure property, that is arrangement of nucleons in the shells, and that is explained by the second nuclear model, that is nuclear shell model, which explains the stability on the basis of magic numbers, that is either proton or neutron number is equal to 2, 8, 20, 28, 50, 82 and 126. So either proton number equal to these numbers or the neutron number is equal to these numbers, then such nuclei are called as magic nuclei, and generally it is considered as the stable nuclei. If both are magic numbers, then it is exceptionally stable and they are called as doubly magic nuclei. Then for the completely filled shells, the spin or angular momentum is 0. Then if we add one more nucleon, so that nucleon is responsible for the spin and parity of the nucleus, which can be determined using this shell model. Along with that, this shell model also explains how much of energy required to move a nucleon from one shell to another shell. So because of that moment, how the quantum numbers change can also explain with the help of this nuclear shell model. So with this, we have completed our discussion on these nuclear models. So in the next session, we will have a discussion on the nuclear instruments. Thank you.